Professor James Peebles. Welcome to the Bagel Table.
Thank you.
This is Montreal's premier conversation over bagels, where we talk about science. And so I guess the first question that I have is, what are you spending your days thinking about now?
Well, I've been retired for 20 years, so I spend a lot of time thinking about a nice walk in the park. But I still come into the office, and I like to come in and think about things. So I'm thinking in two directions. First, a long-standing interest in how galaxies formed. There's a lot of information on the properties of nearby galaxies that I think the people who work on this subject of galaxy formation aren't as familiar with as they ought to be. Yesterday, I stressed some of the beautiful images of nearby galaxies. They contain a lot of information about a particular galaxy. Now, of course, it's a problem that each galaxy is like each person. Each one is different. But they have broad similarities, as do people. And from those broad similarities, you learn some interesting lessons about the actual properties of nearby galaxies. There's also a hazard, of course, because if each galaxy is different, how do we know that the nearby ones are a fair sample of what galaxies are like? And in fact, we know they're not a fair sample in the sense that they're missing the most massive galaxies. But still, these are real objects, and they therefore have some sort of lessons to teach us about the nature of galaxies, and from that, the nature of the formation process. So I'm spending a lot of time studying nearby galaxies, trying to persuade colleagues to pay more attention to them. So the other thing I'm thinking about is perhaps revealed by these books by an outstanding author. And the whole truth is my summary of what I've learned about the philosophy and sociology of science. At least what seems relevant to me from the standpoint of a natural scientist.
So I suppose since you brought up these ideas that you touched on in your book, you mentioned that sometimes the adoption of a theory predates experimental evidence for that theory.
Right.
So one example you gave is how now we teach dark matter even though we have only indirect detections of dark matter.
Yeah.
And how you were taught general relativity before some of the really hard-hitting confirmations of general relativity.
Yes.
So what are the theories that you think are in this strange gray zone in cosmology right now?
Well, I object to strange. I think it's always been the case that we've had bits of science that are well tested and accepted as canonical because they are well tested. And always human curiosity drives people to look ahead. What else can we learn? And of course, new ideas, almost always, are just that, ideas, thoughts. They're not tested, and so it's a mistake to think of them as established science. It's a subtle problem that we have in communication to the public, I think, that we claim on the one hand that our science is hard and objective, it's a fact, physics. We can get very pompous about that. In physics, in natural science, we have evidence that can lead us to conclude that we have a good approximation to some issue. Really convincing because it's tested so many ways. But that's never a proof. Mm-hmm. And along with that is the fact that we have a body of physics that is conveniently called canonical physics. It's a physics that is standard and accepted by everybody. Much of that physics is very well tested. Some bits and pieces are not. And they're put in there for irrational reasons, if you like to think that we're searching for absolute truth. But of course, we search for absolute truth, but we'll never find it, because any evidence has to be of limited accuracy. So we'll never know. I hope that's not considered a dismal thought. I think it's wonderful to think that we'll always have the question, what goes next? How do we improve our theories? And I think as long as the human race is interested in such things, we'll have theories of increasing accuracy and detail, but they'll always be incomplete.
So on the topic of incomplete theories, or moving or attempting to move towards the truth, sometimes we make very good approximations. Preemptively, we define a theory, and then it turns out to be a very good approximation of the truth.
Yeah.
But there are other examples where we just went horribly wrong.
Right.
For example, the one that always comes to mind is the luminiferous ether, where we really got that one totally wrong.
Right.
So is there anything just that you have a hunch that perhaps we've been including in our standard concordance models of cosmology or of astrophysics that might be disproved or ruled out soon?
Yes. I don't imagine there's anything quite as prominent as the luminiferous ether. We remember it was in the middle of about 150 years ago, Maxwell decided to put aside his search for the mechanical model of the ether and instead collect the evidence people had for the properties of electricity and magnetism, made it complete by a few bold assumptions, and gave us the theory that allows all of electricity to be dealt with in so many ways, so many applications. I find it a little hard to believe we're that far astray now, but I know for darn sure that there are elements of our canonical physics that are not right. Mm-hmm. I know that on general principles because we do get enthusiastic and add to our canonical physics ideas that are beautiful and ideas that are in fact fated to be disproved. So we have the idea of cosmic inflation, which is a wonderfully elegant answer to the question, so what was the universe doing before it was expanding? Here's an answer. It's very elegant, but it's been on the books for 40 years. Only I in this room is that old. And I'm twice that age, but still. For half of my lifetime, almost, we've had the idea of inflation. It's taught in school, in universities. But the evidence that that's what really is a good approximation to what really happened is very sparse. We have the negative evidence, so show me a better theory. I don't think it can be done, so I don't think it has been done. That's evidence of a sort, but it's not anything that I would want to put money on. So there it is. We have a beautiful idea. It's canonical, but it's dicey. It is very hard to get people to understand that evidence against a theory in some application is not evidence against the notion that this theory is a good approximation. It's simply evidence that if you push that theory too far, it will fail. Not that it does a brilliant job where it's not pushed so far. Electromagnetism is a brilliant example. Our entire culture depends on the treatment handling of electricity and magnetism by the rules of Maxwell's equations. Try to imagine our civilization without that. But yet we know that if you try to apply Maxwell's theory to the structure of an atom, you go dreadfully wrong. That didn't disprove Maxwell's equations as applied to the currents that are turning on this light bulb. Maxwell's equations are spectacularly successful, but incomplete. And so we have quantum mechanics. We have a better theory, quantum electrodynamics. It's spectacularly good, but incomplete. Then you have electroweak symmetry breaking and on and on. And I see no reason to think that will ever come to a conclusion with a final theory.
Yeah, I suppose you never know if it's just physics all the way down.
All the way down. You know about turtles all the way down. Yes, so this is the same idea.
And even when we do start to get things right, it seems like now our theories are getting more and more complicated, that even to design an experiment to be able to test them, it's becoming more and more strenuous. Like GR took over 100 years for some of GR's predictions, namely gravitational waves, to be verified.
Yeah.
So do you have any worries about physics as a whole in this regard?
Of course, there's two parts to this. Our theory is getting more complicated, and our theory is getting more and more difficult to check. On the complication side, I remember reading that when Maxwell put aside the search for a mechanical model of the ether and wrote his equations, he wrote them in an awkward way, and it is recorded that many physicists were just distraught over trying to understand what Maxwell was doing. But then people learned how to streamline the description of Maxwell's equations. So until now, well, maybe they're not appropriate for high school, but they're not all that hard. I think the same thing tends to happen. A theory may be introduced in a complicated way with notation that's not very appropriate, and that things can simplify. So far, that's been an awfully good rule. And you mentioned Einstein's general theory of relativity, 100 years old and more. It was said, well, only 12 people understand the theory. And of course, I don't know if that's realistic or not. It was a complicated theory to begin with, and still is, but of course our notation is streamlined. That was done very quickly. And now I think it is not so hard to deal with. After all, it's simply a field theory, like Maxwell's equations. You go from a vector to a tensor field. It's a natural extension. And remarkably enough, through my career, I was always wondering, am I making a big mistake by assuming that Einstein's theory applies on the immense scales of the universe? It wasn't at all obvious to me. But to my amazement in recent years, it's been wonderfully successful. Now, then the other side of the point I think is very relevant. The easy experiments, the low-lying fruit, so to speak, have been done, I think. Not always for sure, of course, because there are so many aspects to the world around us that it's hard to know whether we've thought through everything. Are there simple experiments that still can be done? Well, an example that I like to pester my colleagues with is, have you looked at some images of galaxies on the web? And sometimes there's a slightly embarrassed silence. But in general, the trend is pretty clear. You don't do particle physics anymore without $1 billion or many, probably. They've answered the hard questions already. Now they got the ultra hard ones. So you can well imagine that there will be theories that are elegant and seem very persuasively constructed that the world economy cannot afford to test. Mm-hmm. That is the end game. Natural science in that field will have ended, in my point of view. But don't despair. There's an enormous number of directions to look to expand our knowledge. Yes, I think it's true. We must anticipate that the end game of natural science will be inability to test.
So,
don't panic though.
Yes. So before I panic about my graduate degree,
yes.
If you were in my place now and you were a graduate student studying cosmology, what would you study?
I don't know. So I would go into a less explored subject in cosmology, but I would be very careful to make sure that it's not less explored because it's been ruled out by evidence. Mm-hmm. That's a hazard that people don't always pay enough attention to. But still, there are directions to go in cosmology that would be attractive to me. But of course, the great new advance in physics is going to be biophysics. How in the world are we made? Do you know there are slime molds that creep along the ground? There are an enormous number of single-celled entities that move around eating, and then when they decide they've had enough, they make fruiting bodies. How in the world do these single-cell entities manage to do that? I mean, I ask you. And you know, we have butterflies, monarch butterflies, one branch of which migrates south through New Jersey and along the coast. They come to the tip of New Jersey, which is a peninsula, Cape May, and then there's a 10-mile or so flight over to Delaware. And we once were visiting this small park at the tip of the New Jersey, the tip of Cape May. We come across trees just covered with monarch butterflies. So we asked a ranger, what are they doing? And he said, they're waiting for the wind to change to blow them across to Delaware. I mean, I almost fell over. This is a purposeful decision. Let us wait until the wind is right. Now, you and I might decide to do that, but how do those butterflies manage it? I can't imagine.
Incredible.
But it does teach me that complexity obtains at the level of a butterfly. Deep complexity which we will be exploring. It is the next step. Of course, the public pressure to cure my disease is so pressing. There's so many diseases. But to understand that disease really well and how to treat it, you have to understand how things work on the molecular level.
Right.
And that's really, really complicated.
It is. I have the great pleasure of sharing an office with the biophysics group, and I am amazed by what they do.
Yeah, it is spectacular. And the motivation, the intellectual interest, it's spectacular. So that is going to be the subject of the century. But you and I are secure in cosmology. There's still a lot to do there.
Thank goodness, because I really was worried there for a moment earlier. Do you have some favorite advice for younger students?
Well, no. You know, the situation evolves, and I don't. So probably any advice I would offer is obsolete, except for the most general of generalities. Try to find something that really interests you and can be turned into a career. I think I was dead fortunate in that I have very simple tastes. I love physics. I didn't know that until I was at the University of Manitoba. And you mean you can actually make a living doing this? I didn't know that until university. And I discovered it was really to my taste. You know, I began in engineering because I knew I liked to build things. And then I discovered one there that I was running out of the courses that were my favorite, so I transferred to physics. It just drew me. I never made a conscious decision, I want to have a career in physics. It was there. If you're fortunate to have that inclination, then by all means pursue it.
Yeah, and I've noticed, I mean, I relate to you a lot on this point because I had the same experience of starting university in something different, and then physics just grabs you somehow, and you make the switch and you never look back. But do you have any advice for later career scientists for how to achieve such a long career?
Oh, well, first stay healthy. Lots of luck. I can take no credit for lack of serious physical disability. I don't think I was particularly careful with myself. You know, the Burns, Gracie Allen, he lived to a great age, and he said to the remark, if I had known I was going to live so long, I would have taken better care of myself. And that's now my situation. So it's pure dumb luck, and I guess some degree of refraining from smoking, for example. But the one big piece of advice to anyone who's approaching retirement have a good plan for what you're going to do when you retire. I've seen examples of people who retire, thank God that's over, but what do I do now? Horrible. Luckily, I knew what I wanted to do. I don't want to do any more committees. But other than that, I just want to keep doing what I love to do.
What was the proudest moment of your career for you? Is there one in particular that stuck out?
No, right now.
Right now.
Yeah, I made it this far.
And that's great. We're so happy.
It's rather like asking which of your children is your favorite.
Oh.
You can't answer that.
So every moment doing what you like is the best.
Right.
That's a great answer.
I just made it up. Actually, I made it up yesterday.
So one thing that you touched on earlier, which I was very curious about, is that you like to stay by yourself and you enjoy that time alone.
Yes.
And I've had some of my friends who are also in astronomy and cosmology, but more on the observational side, say that they have this very deep connection, this very, profound, warm and fuzzy feeling when they look at the night sky in an environment like that. But strangely, I've never had that experience. But rather, I do feel that sort of connection, let's say, when I'm sitting, working on my problems, or reading a great textbook, or thinking about what the early universe must have been like. So I was wondering if you have, what your relationship is with the night sky.
It is very similar, I think. I grew up on the prairie, and I remember nights where the sky was just glowing with stars. Isn't that beautiful? And I remember, of course, the aurora, which at times can be spectacular in Manitoba. But I never cared to distinguish, is that a star or a planet? What is the name of that group of stars? That never interested me. But I certainly love nature in all its manifestations. It's gorgeous, love it. But no, I don't have the inclinations of a real observational astronomer. I can't name any object up there except maybe the moon. And the sun, I got that one right. But the stars, they're nice, but on the other hand, there are some galaxies I've grown to love because they look so enigmatic.
Interesting. Yeah.
Well, we all have our inclinations, prejudices, preferences.
So last but not least, we have a rapid fire section.
Okay.
So first, what is your favorite Canadian city?
St. Vital, Manitoba.
What is your second favorite Canadian city?
Winnipeg, Manitoba.
Amazing answer.
The third is Montreal.
Wonderful answer. Do you have a favorite book?
The one I'm reading. This is my new style of answering.
Yeah, the current one.
Yeah.
Do you have a favorite beyond lambda CDM theory?
No. My favorite book is Landau and Lifshitz' Classical Theory of Field.
Ooh.
I did 1951 edition.
So all students, you have to get Landau and Lifshitz.
Oh, valuable.
Yes, that was my textbook for when I was an undergrad as well, actually.
Oh, yeah.
What is your favorite cosmological probe?
All.
Oh, very good answer. If you had to pick, which Hubble constant do you prefer, 68 or 72?
70 plus or minus 2.
Very good. This is incredible. And with that, thank you so much for sitting down with us at the Bagel Table today.
It was fun.